We now know the fundamentals of using ANOVA, the analysis of variance. These skills are going to carry us far because we're going to be applying everything we've learned about the fundamentals to 3 different designs. The designs that we're going to learn about are, number 1, the completely randomized design. This is the one-way ANOVA. This is similar to, or really a repetition of, what I showed you in the last lecture. Except we're going to go through a little differently. I'm going to be using Excel, and I'll show you how we could do a Fisher post hoc test for this design. Now, the second design that we're going to use is called a randomized block design, which is very similar, or really the same, as a repeated measures design. I'll walk you through the basics of blocking and why we do that and how we're controlling for the variability created by these blocks. And then the third one is called a factorial experiment. You remember with the one-way ANOVA, we only had 1 independent variable. With a factorial experiment, we can have 2 independent variables and see how each one of those influence an outcome. And more particularly, if they influence an outcome in such a way that we have an interaction and the outcome is different for different groups. How are we going to do this? Let's get a business of the week. And the business of the week is Tsarbucks coffee. From this business of the week, you may get a hint as to where I hang out when I'm trying to come up with examples to use for my business statistics class. Sit around and drink a lot of coffee to stay well caffeinated as I'm looking for creative ways of illustrating topics like analysis of variance. And that's what happened here. Tsarbucks employs coffee bean scientists to grow the best beans possible. Horticulturist and statistician Juan Valdez conducts a variety of growing experiments on coffee bean plantings. We're going to have different factors. We're going to have outcomes. One of the things that will vary in our analysis of variance is the type of coffee bean. So our first factor is type of coffee bean, Arabica, Robusta, and Liberica. We're going to have a second factor, which is location. We're going to grow our beans in different places in the world: ancient grounds, equal exchange estate, and purgatory plantation. And these are located in places that maybe are low altitude and cool, or maybe low altitude and warm, or high altitude and cool. So we're going to see different types of beans grow differently in those locations. And then a third factor that we're going to consider is, does season also function as a factor? We'll have 3 planting seasons: late spring, summer, and early fall. For all of these examples, we're going to use the same outcome, and that would be yield, tons per hectare. Our dependent variable is going to stay the same for all of these examples. It's going to give us a really clean design and allow us to do comparisons between the models as well. There are extraneous variables, things that we can't control for, things like rainfall, because some years you get more rain than others, the amount of sunshine, where in particular beans are planted in a specific location. Maybe there's one part of the estate where the coffee beans get a little bit more sun, or they have a little bit better drainage. That's going to make some kind of difference in the outcome. Now, these extraneous variables are all going to get subsumed, they're all going to get wrapped up in what we call error. Our error term is all of the variables that we can't control for. So we're going to extract the amount of error, and then we'll extract other sources of variance in order to really be able to focus on our treatment effect. And that's what we're most interested in. We'll identify what is the thing that we want to know that influences outcome, and we'll try to get rid of all of the other variability so that we can exquisitely focus on those treatment effects. The first design that we're going to look at is the fully randomized design. In this case, we're going to be examining what happens to yield based upon type of coffee bean. Do certain beans grow better than other beans? And here's our setup. At the ancient grounds, Juan Valdez plants Arabica, Robusta, and Liberica coffee beans. Are there differences in yield between the 3 types of beans grown in the same soil? This is called either a completely randomized design or a fully randomized design. Those are two names for exactly the same thing. They're both focusing on the randomization within your model. What that means is we have random selection and we have random assignment. Random selection, all of the individuals, all of the coffee beans in the population have an equal chance of being selected. And once they have been selected, all of those that are selected have an equal chance of being in one of the treatment conditions. Because we have random selection and random assignment, we have a fully randomized model. So if you hear me say completely randomized or fully randomized, I'm talking about exactly the same thing. So let's walk through our 5 steps of hypothesis testing and learn how we can determine whether coffee bean yield is different based upon the type of coffee bean. Step number 1 is we're going to select the appropriate statistic. For this example, we're going to keep location constant. So what that means is we're going to grow all 3 types of beans in the same place, in the same general location. But as we've talked about with other examples having to do with growth, the fact that you're planted on this side of the field versus that side of the field, that could also account for some variability within, and we're going to extract that using our error term. So let's see what we have. We're going to plant 3 types of coffee beans in a similar place on the grounds here at ancient grounds where we're growing these coffee beans. It's low altitude and cool. And you can see from the color of the soil should be the same for all of these beans. We have 3 types of coffee beans. There's Arabica, Robusta, and Liberica. Do any of these beans grow differently based upon their location? Now, I'm not just going to plant 3 beans. I'm going to replicate this 7 times so that I have multiple growing locations, which when it comes to coffee beans are called poles. So a plot where you grow coffee bean, that's a pole. Are there differences in outcome among the 3 beans grown in the same soil? All of the beans have been randomly selected. They have been randomly assigned or planted in their respective pole. We have a lot of variability to unpack. So let's walk through how did we choose this design, this one-way ANOVA, or this fully randomized design? Well, we chose it because we have an independent variable with just one factor, type of coffee bean, and that factor has 3 levels, the 3 specific types of coffee beans that we are planting. Our dependent variable is always going to be yield. It's the amount of production. It is something that can be measured with a mean because it's a category, because it's a continuous variable. Starts at 0, goes up from there, equal intervals between 1 pound to 2 pounds or 1 kilogram, 2 kilograms. There is a scale underlying our measurement. And because we have an independent variable with 3 groups and we have 1 outcome, that's our setup for this fully randomized ANOVA, or one-way ANOVA. I've been telling you about analysis of variance. Well, let's talk about the sources of variance, and particularly the sources of variance that we can't control. When you think of the model for an ANOVA, you could think about a pie. Not the Greek letter, but the actual pie, like it's Thanksgiving. And we have a pie, but at this Thanksgiving, we also have an unwanted guest called error. Now, this is a guest that comes every year, so we always know error is going to show up and eat a certain amount of our pie. But what we want to do through skillful research design is maximize the amount of variability due to the treatment effect and minimize the slice of the pie that we're going to have to give to error. We'll divide up the total variance in the data into the parts that are due to treatment effect and the parts that are due to error. And our question is, how big of a slice do we have to cut for the error? Is the slice that we cut for ourselves, the treatment effect, large enough to find differences between the levels of our factor? Let's take a look at the data that we're going to be using. And look at the structure of the data. Because I'm going to be using Excel for this example, I'm structuring them in a way that does work for Excel, but it doesn't really work for JASP, SPSS, R, some of the other statistical software that we could use. I'll show you an example of how we would structure our data if we were using JASP, but for now we're just focusing on Excel, and Excel does things a little differently. What you can see is we actually have 3 columns. The header for each column tells you the type of bean that is being planted. These are the 3 treatments, the 3 levels of our single factor, which is coffee beans. Our dependent variable is the yield, and we can see that between the means. We have different yields, different amount of growth for each of the 3 coffee beans. The question is, are those differences large enough for us to say that one is truly better or grows better than another? And then we have the total amount of variability within our whole model. We're going to have variance within each bean. We're going to have variance between the groups. And we're going to have all this total variance that just concludes all of the within and between. We're going to have to separate out the part that is due to error versus the part that is due to our treatment effect. We're going to want to focus on that treatment effect and see if there's evidence to say that there are true differences hiding among our groups. Step 2, let's establish the null and the alternative hypothesis. In this case, we're going to assume that all the beans grow equally well in this location. There's no difference in yield based upon type of beans. All of the beans are drawn from populations whose means are equal. Therefore, we're going to structure our null hypothesis as H sub 0 colon mu1 equals mu2 equals mu3. Outcome for each level of the factor is the same. Our alternative hypothesis will be H sub 1 colon mu1 does not equal mu2, does not equal mu3. There are differences in the yield among some of these beans, and we're going to have to figure out where those differences lie. Step number 2, we'll select our criteria for significance. This one's pretty easy. We're going to keep our significance level, our alpha level, set at 0.05. This is typical for any type of statistical analysis that we're going to do. And this is where I usually tell you about one-tail and two-tail tests. However, the ANOVA F test is not a one-tail, two-tail possibility. It's all one tail. Because of the squared values, there are only positive numbers in our F test. What we're going to be looking for are differences from 1. So if there is no treatment effect, our F value would be 1. If we see differences larger than 1, now we have some kind of treatment effect. Is it large enough to get over that fence? We're not going to think in terms of one-tail or two-tail tests. We're simply going to think in terms of, is there a difference? Evidence to find differences among our 3 levels. The degrees of freedom will depend upon between, within, and total. The degrees of freedom between is k minus 1. That's the number of groups minus 1, or the number of coffee bean types minus 1. We have 3 types of coffee beans. The degrees of freedom between is 2. Degrees of freedom within is n minus k, or 21 total coffee plants being planted minus the 3 groups for a difference of 18. And our degrees of freedom total, as it always is n minus 1. We have 21 total participants, we'll think of them as. Therefore, the degrees of freedom total will be 20. We need to look up a critical value for these degrees of freedom. We have 2 separate degrees of freedom we're going to consider, between and within, and we could look them up in an F table. Or we could save ourselves some time and use a spreadsheet that I've created for this course and for this week, and we'll just enter our degrees of freedom in Excel, and Excel will tell us what is the critical value that we're shooting for. What is the fence that we want to get over that will tell us that there really is a statistically significant difference among our groups. So what we would do is go to the critical value effect size tab, and near the top you'll see this critical F value for alpha 0.05 two-tailed test. I guess we can kind of ignore the two-tailed and also point out that that 0.05 can be changed. If you want to use a 0.01 or 0.1, you can adjust that here in the alpha level box. We're going to keep it at 0.05, and we're going to enter the degrees of freedom between as 2 and the degrees of freedom within as 18. And we get the answer 3.55 as our critical value. That is the value that we're trying to get beyond so that we can determine statistical significance. Once we've done that, it's time to calculate the test statistic, and for this we're going to be turning to Excel. We're going to be using the analysis tool pack for this example. There are multiple ways of doing ANOVA in Excel, and there's also multiple statistical programs that we could use. So we're going to take one specific approach using Excel with that analysis tool pack. So let's take a look at how that's going to work. To use the analysis tool pack, we're going to go to the Data tab and click on Data Analysis. Of course, this works if you have the tool pack installed. We have a variety of analyses that we can do. You may need to scroll up or scroll down, but find at the top of the list of analysis tools, ANOVA single factor. And then click OK. This brings up a dialog box that we can then use to identify the range of the values that we want to go into our ANOVA. So first of all, we're going to grab the input range, and for this example, we can't just select all of the columns of data. We're going to want to be very specific. So get D3 through F10, which includes the headers and all of the numbers in our data set. The data have been grouped by columns. The header is at the top of the column. The data are underneath the header. So grouped by columns and labels in the first row. We're going to keep our alpha level set to 0.05. However, if we had a different standard for statistical significance, 0.01 or 0.10, we could change it here. For the output range, click first on the radio button for output range, and then on C16. And you can see where that drop zone is supposed to be. And click OK. Excel is going to cuss at you because there's already information here. We know that. I put that information there. There's something we're going to overwrite. That's OK. So click OK, and let's take a look at our output. Here is the output for that one-way ANOVA. We'll notice under the summary that we have counts, the size of each group, each level of our factor, sum, averages, we're going to need that for comparison later on, and also our variance. Remember, this is an analysis of variance. There's our variance measures. But also remember, if you're ever looking for the standard deviation, this is the variance, not the standard deviation. You're going to need to take the square root of the variance to get to the standard deviation. The rest of the findings give us the sum of squares, degrees of freedom, and mean square, which looks a lot like that ANOVA summary table that we've seen before. And in fact, we can use this information to cut and paste into an ANOVA summary table that we could then use for a publication. To the far right, we see the critical value. We looked that up in a table. Just remember that in the ANOVA summary table, we usually put a measure of effect size on that far right end. And this is not that. This is not effect size. This is the critical value that we actually looked up earlier in this example. But the information that we're most interested in is whether or not our test is statistically significant. We have an F value of 7.21, which exceeds our critical value of 3.55. It is over the fence. we have a p-value of 0.01, which is less than 0.05, or 1 penny less than a nickel. So both of these tell us the same thing. There is a statistically significant difference among the yields for the 3 types of coffee beans that we have selected. There are differences, and we need to find where those differences lie. And for that, we're going to need to do a post hoc test. The type of post hoc test that we're going to do is one that is suggested by our textbook, and it's called Fisher's LSD, the least significant difference. Why are we doing this? Because the F test is an omnibus test, which says there are differences in here somewhere. But we don't know exactly where. We need to do a follow-up test to determine which group means are different from which other means. You may remember that I described Fisher's least significant difference test as having the same number of type 1 errors as a t-test. And that's because really that's what this is. We're doing a t-test as a follow-up test. We usually do a t-test at a 0.05 level, but because we're only looking for one tail, we're going to divide that in half. We'll be looking instead of 0.05 for 0.025. And what we would do is look up a value on a t-table, or we can find it in a spreadsheet, for a t-test with 0.05 divided by 2, or 0.025, alpha level, at the same number of degrees of freedom as are within groups. So we have 18 degrees of freedom. Plug in that 18 for our spreadsheet, we're going to get a 2.101. That is what goes in this part of the equation, 2.101, times the square root of your mean square within, 11.29, times 1 over each of the 2 sample sizes. And for that, we get an outcome, an LSD value of 3.773. Now, at this point, you may notice that we're only comparing two group sizes, and yet we have 3 groups total. What's going on here? The answer is that for a least significant difference post hoc test, we will compute a different least significant difference value for each of the group comparisons. Right now, we're comparing group 1 to group 2. We would have to calculate a different LSD value for groups 2 and 3, and for groups 3 and 1. However, in our example, all of the groups have the same size. So in this particular example, we're going to use the same LSD value. If the groups were of different sizes, one has 7, one has 8, one has 6, we would need to calculate separate LSD values for each of those comparisons. Look at the post hoc tab, and let's see what information we need to find. You'll first notice that we need the degrees of freedom error and the mean square error, both of which can be extracted from our F table. We'll enter 18 for the degrees of freedom error, or degrees of freedom within, and we'll enter 11.29 for the mean square error. For this next part, we're going to do some copy and paste, and I need to point out to you that there's a space for sum in this table where we're going to paste, except we don't need that value for this test. What I've done is design this spreadsheet so you can simply copy and paste. So let's look at our F table, select all of the data from Arabica over to the average for Liberica, which is 13, grab all of that, copy, and then paste where it currently says group 1. Let's look at the comparisons now. We can see group 1 versus group 2 has a mean difference of 4.86. Well, where does that come from? The mean for group 1 is 6.43. The mean for group 2 is 11.29. Subtract those two and you get a difference of 4.86. And notice that I'm using the absolute value. We're not concerned with one group being larger, smaller, positive, negative. We're simply looking for a mean difference. And we're going to compare that mean difference to our Fisher's LSD value of 3.773. Any values greater than that Fisher LSD value are significant. 4.86 is greater than 3.77. Over the fence, it is statistically significant. When we look at the group differences for group 1 versus 3, that's 6.57, also greater than 3.77. That is statistically significant. And then finally, 1.71, the difference between groups 2 and 3, is not over the fence for 3.77. It is not statistically significant. So let's walk through how we could think about these mean differences. Obviously, you can see the findings in the table, but I want you to understand the comparisons that we're making. Let's start with this. The rejection rule is going to stay consistent. Anytime we find absolute value differences greater than 3.773, we have statistical significance. When we compare Arabica versus Robusta, the absolute value difference between those two is 4.86, which is over the fence of 3.7. The population average yield for Arabica is not equal to the population yield for Robusta. They are different. Our second comparison is Arabica versus Liberica. And we find that their mean difference is 6.57, which we compare to 3.773. It is over the fence. So the population average yield for Arabica is not equal to the population average yield for Liberica. They are different. Our third comparison is between Robusta and Liberica. We find a mean difference of 1.71, which is not over the fence of 3.773. Those two numbers are equal. Or we could say it more simply by concluding that Robusta and Liberica both differ from Arabica. But now we need an effect size to determine just how large this difference really is. Let's go to the tab that says CV and effect size. It's the same place where we found that original critical value. Scroll down just a little bit until you find fully randomized ANOVA. So you'll notice there's a place where we could paste some information. And when we do that, we're going to see the effect sizes over here in the boxes to the right. Well, where does that information come from? That comes from the output that we just created using the tool pack. Select the numbers from the sum of squares between groups all the way down to that blank box in the lower right. Copy. And then jump back to the critical value effect size tab and paste those values where you see the sum of squares treatment. Once those numbers have been pasted in place, you will see two measures of effect size, eta squared and omega squared. Now, both of these are legitimate measures of effect size. The difference is that the eta squared is telling you the effect size for your sample, which is interesting, but what we really want to know is the effect size for the population. Therefore, we're going to report the omega squared. And notice that for a one-way ANOVA, or fully randomized ANOVA, both partial eta squared and eta squared are the same. Both partial omega squared and omega squared are the same. Therefore, we are simply going to report the omega squared effect size of 0.372, which we can interpret using this handy guide at the bottom as being a large effect size. Now that we have that information, step 5, interpret the results and write up the findings. Let's quickly review what we've learned so far. First step, is there a statistically significant difference in our model? We calculated a critical value with 2 and 18 degrees of freedom at 3.55. Our F statistic is 7.207, which is over the fence of 3.55, statistically significant. We calculated a probability value of 0.005, which is less than a nickel, less than 0.05. Both of these tell us the same thing. We have a statistically significant difference. We reject the null hypothesis that says there are no differences. We accept the alternative hypothesis that says that those differences exist. We had to do a post hoc test in order to determine which groups were different than which other groups. And having done that, we're able to determine that we had two types of beans that grew about the same, and then one that grew really much worse. We're going to see that information coming up again later as we go deeper into the modeling that we're going to create. To do an APA-style write-up, we would create an APA summary table that looks like the one you see here. I've called this treatment and error as the source of variability, although we could call that coffee bean and error if we wanted to write it out that way. The APA-style write-up is in your notes. And if you want to see that and look at that in detail and study that, you can find it there. And that, my friends, is how you do a fully randomized ANOVA. Next, we're going to look at what is equivalent to a repeated measures, but we're going to call it a blocked ANOVA.